Now sometimes they will give you a question like they will provide you the bending stress distribution for a particular section, and the section they will not provide. In that case, you have to identify where the neutral axis will lie. Second type of question is that they will give a section and the bending stress distribution or a bending moment will be given. We can calculate the maximum stress on the top and bottom fiber for the given section. In that case, they will show some area on the section and we need to find out what is the force exerted in the horizontal direction for the given section and what is the percentage of moment resistance for that particular hatch area. So we'll consider here one unsymmetrical section. So for the given figure here, the centroid will lie somewhere here, that is near the bottom. So this one is the same as centroid G. In regular practice, we'll fix up our z-axis as a horizontal axis and the vertical axis as y-axis. So this one is a given beam here and is subjected to moment m. Now if we have shown this type of moment, it means that you have to take the value of bending moment m as a negative value, and this one is representing the case of hogging. So because of a hogging here, the beam will take a shape something like this. Because of this shape here, our top fiber will be in compression and the bottom fiber will be in tension. So on the top we'll get a negative value of a stress and at bottom we'll get a positive value of a stress. And if you come across this type of situation where the beam is subjected to bending moment m, will be taken as positive value, and this one is representing sagging. Because of sagging here, the beam will flex in this fashion. This one is the bottom fiber and the top fiber will get this shape. It may the length of the top fiber is increased and the length of the bottom fiber is decreased. So in this case, we have tensile stress on the top and the compressive stress at the bottom. So depending upon the hogging and sagging condition, they will provide you the distribution here. So suppose they provide this type of distribution and we have shown the bending stress on the top fiber on the right side. It means that we have tensile stress on the top and we have the compressive stress at the bottom, and they will provide the distance equal to y1 of the top fiber and the total distance equal to y. In that case, it will cross at this point. So this one is the position of a neutral axis. Let's say this value is equal to y2 and the value of y2 will be same as equal to y minus y1. Question asked here, where is the location of neutral axis? So they ask you what is the location of neutral axis. It means that we have to find out the value of y2. Since here we have a linear distribution of a stress, we have the sigma b on the top divided by sigma b on bottom is same as equal to its distance from the neutral axis. So this one is representing the neutral axis. For top it is proportional to y1 and for bottom it is proportional to y2. And we can very well solve this value of y2 because y2 is same as y minus y1. So there is only one unknown and we are comfortable to find out here the value of y2. So this is one type of question they can ask you. So if you find out the value of y2, then the position of neutral axis can be obtained. Second type of question they will ask you, they will give some area, that is this area, and they will ask you how much is the horizontal force is exerted on this area. So your first job is to find out what is this area A. Then you have to find out here what is the average value of a stress here. Let's say here this stress at the top fiber for the given section will be equal to sigma A, and for bottom fiber for the given section we have this stress equal to sigma B. Now we know the distribution here, and using the proportional distances of YA and YB, and from the same neutral axis here the distance equal to YA, and here we are knowing here that the sigma T, that is the stress on the top fiber divided by y1, is same as the stress at point A divided by YA is same as equal to the stress at point B, which one is the bottom fiber of the given cross section, divided by YB. So for given cross section here there is a basically variation in a stress. Once we are able to find out the magnitude of sigma A and sigma B, we can have to find out here the average value. Average value here is basically the sigma A plus sigma B divided by 2. So we can show here a rectangle, and on this rectangle we have a average distribution, and this average distribution, because of a linear profile, we have sigma average will be equal to sigma A plus sigma B divided by 2. Once we have a average distribution is known, we can find out the force here. So horizontal force exerted this time will be equal to sigma average multiplied by given area A. In this fashion, for any cross section, we can find out the force exerted on any strip. Suppose they say what is the total force exerted from neutral axis up to the top fiber, then you have to consider neutral axis stress equal to 0 and the top fiber equal to sigma t. On an average we have sigma t plus 0 divided by 2, that will be the average stress multiplied by the area above the neutral axis. In this fashion we can calculate the force. And the third type of question, they can ask you what is the moment resisted by the given cross section. So this time they will provide that we have this cross section here, and this cross section is from the neutral axis NA at a distance equal to YA and distance equal to YB from the neutral axis. Now here the distribution is going to change from YA. At YA we have a stress equal to sigma A. At YB we have stress equal to sigma B. And since we are interested in the moment is defined here as a force multiplied by the perpendicular distance from the neutral axis, that equal to y. Now since here there is a variation of the stress and its distance from the neutral axis, what we'll do here, we'll consider here one elemental area. So we'll consider here one elemental area, and this elemental area is a very small area. Let's say this area equal to dA, and correspondingly we have a stress on this one is equal to sigma. Now this value of sigma at any distance y from the neutral axis can be computed using the distribution. So first formula you have to use is that the maximum stress sigma t, which is at a distance equal to y1, and for given elemental area A we have a stress equal to sigma, which is located distance equal to y from neutral axis. Now this time we can calculate the value of sigma is equal to sigma t divided by y1 multiplied by the distance equal to y. Now we can compute the force for the given element. That force will be equal to dF is same as equal to sigma multiplied by area dA. And then we can calculate the moment resistance for the given area will be equal to dF multiplied by y. And then we can calculate the total value by substituting the value of dF, and we here will put the value of sigma. So we have sigma is replaced as sigma t divided by y1 multiplied by distance y, and this value is y, so we have y square multiplied by dA. Now this value of dA again you have to approximate equal to constant value of b into dm, and then you have to integrate this value from dm from y1 or from YA to YB. So you have to integrate this from YA to YB. In this fashion we can calculate here the moment resistance for the given cross section, which is distance equal to YA and YB from the neutral axis. A structural beam subjected to sagging bending, it means that we have positive value of bending moment as a cross section, which is an unsymmetrical I section. In the case of unsymmetrical I section, the stress on the top and bottom fiber are different. The overall depth of the beam is equal to 300 mm, that is from the top fiber of the top flange and the bottom fiber of the bottom flange. This total distance equal to 300 mm. The flange stresses in the beam at the top flange is 200 megapascal tensile and the bottom flange is 50 megapascal compressive. What is the height in mm of the neutral axis above the bottom flange? So we have given here the stress distribution. At the top flange we have tension and the bottom flange is equal to 50. We have tensile stress on the top fiber, and let's say this value of tensile stress as given to us is positive value is equal to 200 megapascal. And at bottom fiber here we have sigma at bottom fiber is compressive in nature, and this value is equal to 50 megapascal. So sign convention will not follow. So to find out the neutral axis here, we'll join the tip of the tensile stress with the tip of compressive stress, and where the distribution line will intersect to the vertical, so that will be the location of neutral axis. It means that the centroid position is nearer to the larger area. It means that we have larger flange at the bottom and the smaller flange at the top. So since here neutral axis is nearer to the bottom side, it means that we must have a larger flange at the bottom and a smaller flange at the top. So at the bottom we'll show the larger size of flange, and the top will show the smaller size of the flange. So this figure represents here the required unsymmetrical section. He says that the total depth equal to 300 mm. So top of the top flange and the bottom of the bottom flange at distance equal to 300 mm. So this vertical distance equal to 300 mm. What we are interested, what is the height in mm of the neutral axis above the bottom flange? So because of the larger size of a flange, the centroid will shift to the bottom side. Let's say this value is a centroid and corresponding is a neutral axis. And we are interested here the distance of the neutral axis from the bottom flange. So let's say the bottom flange at distance equal to y, then the remaining distance will be 300 minus y. That is the top flange will be at distance equal to 300 minus y. So let's call this value is equal to y1, corresponding stress equal to sigma t. Let's call this distance equal to y2, corresponding stress equal to 50 megapascal. And we have a linear distribution here, so we can use the formula of linear distribution. Sigma t is proportional to y1, so we have sigma t divided by y1 is same as sigma compressive is proportional to y2. So we have sigma compressive proportional to y2. Sigma tensile is same as equal to 200. y1 value is same as equal to 300 minus y. Sigma compressive is equal to 50 divided by y2 value is same as equal to y. So this 50 is get cancelled here, and in numerator we have 4. So we have 4 times of y is equal to 300 minus y. That is we have 5y is equal to 300. It means that we have required distance from the bottom flange of a neutral axis is equal to 300 by 5, that equal to 60 mm. So our answer is 60 mm. 60 mm means our choice B is correct choice. The ratio of the maximum compressive and the maximum tensile bending stress of the beam section subjected to sagging bending moment is 1.75. The depth of the section is 150 mm. The location of a neutral surface from the bottom surface we have to find out. Now what type of section is not known, but the depth is known, that equal to 150 mm. And secondly, we know the ratio of the compressive stress to tensile stress, that equal to 1.75. So we'll consider only the magnitude this time. And secondly, he has given the sagging. So in the case of sagging here, the bending moment you have to treat as a positive value, and initially we have shown the horizontal position. After we apply the bending, in that case the top fiber will be in the tension and the bottom fiber is compression. It means that if we can show the stress distribution, you have to show the value of the stress on the top as a tension and the bottom we have compression. So on the top fiber we have tensile. Tensile will show on the rightward. But in addition to that, we'll confirm the value of the maximum stress magnitude in compression and in tension. So we have maximum value of compressive strength, that is sigma max compressive to the sigma max tensile. This ratio is given to us, and this ratio is given as 1.75, which clearly indicate here that the value of maximum stress in compression is equal to 1.75 times the maximum stress in tension. So according to that, we'll construct our figure. Since we have a compression is more, so what we'll do, we'll show here larger arrow at the bottom, and sigma max tension is a lower value, so we'll show here a smaller length of arrow. So this is the stress distribution here. So bottom fiber we have maximum compressive, which is more as compared to the top fiber, which is maximum tensile, Where it will cut the vertical axis, that will be our neutral axis. So if I draw here a horizontal line, that will represent the neutral axis. What we are interested is the location of a neutral surface. So neutral axis and neutral surface are one and same from the bottom surface. So from this point here, we want to find out here the location of neutral axis. In addition to that, he says that the total depth of the section is 150. So this depth is same as equal to 150 mm. Since we are interested at the bottom, so we'll show this distance equal to y. In that case, the top fiber is the distance equal to 150 minus y. So this value is same as 150 minus y. Now distribution is a linear here, and we know the relation here, that is sigma max compressive by sigma max tensile. Corresponding distances here for the compressive is y and tensile is equal to 150 minus y. So the maximum compressive will occur at distance equal to y from the neutral axis. So this ratio is same as y divided by 150 minus y. Maximum tensile distance equal to 150 minus y. So divided by 150 minus y. Now we have to solve this equation. Cross multiply, you will get the left hand side equal to 262.5 minus 1.75 times of y is same as equal to y. That is, we have 2.75 times of y is same as equal to 262.5. So y distance will be equal to 262.5 divided by 2.75 is 95.54 mm. So our answer is 95.54. So this distance is come out to be 95.54. Which one is the location of a neutral surface from the bottom surface? Exact section we can't show because only the information given is about the depth. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.